Chaitanya Konda, and I work for EY, and very specifically, I work within the EY's blockchain R&D team. Well, I'm here to talk about Polygon Nightfall. Just to probably clarify firstly, why Polygon, why EY, because I seem to be using lots of different company names here, so who do I really work for? Essentially, I get paid by EY, so my salary comes from EY. If I get fired for this, that will be by EY, not necessarily Polygon. On the other hand, why Polygon's involved here is Polygon is the one that is taking Nightfall into the mainnet deployment, and it will be hosting and maintaining and managing Polygon Nightfall as soon as it's launched on the mainnet. And EY will fall back to doing research like we do as always. That's where Polygon Nightfall fits with Polygon and EY. I'm going to be talking a bit about what Polygon Nightfall is, and I will also be doing a very quick demonstration about what it does, whilst also giving you a very quick preview of what the wallet will soon be once it's launched on the mainnet look like. With that, well, very briefly, to put some context to this discussion, Nightfall, or the very first version of Nightfall that came out back in 2018, was built purely with the purpose of enabling private transfers. So we use zero-knowledge proofs for mainly on the privacy end of the spectrum as opposed to scalability. That was the very first iteration. EY wanted to tackle how do we make privacy possible for tokens and how do we get enterprises onto the blockchain network. So with that in mind, Nightfall was essentially built to enable private transfers of ERC721, 1155 tokens, and the sort of anonymity that you get here is of the recipient being anonymous. And you would also have confidentiality of the value or the token that you're transacting or transferring to someone. Now, essentially, there's three different kinds of functions you can do. You'd have deposits, transfers, and withdrawals. Everyone who's been in the blockchain world knows this is the common set of three things that you can do with tokens anyway. Now, just to give a bit of context to what privacy entails here, so deposits are taking your tokens from the L1 blockchain, which is in our case, it's Ethereum, and locking those into a contract that also sits on Ethereum. And this we actually call is the L2, but necessarily it's a very confusing or misleading term. It's not necessarily a side chain. It's just another contract that holds the state data and has this information for blocks of L2, and that's what we call L2, which is a piece of state information held within this contract. Now, when you move a token from the L1 world into this contract, you're essentially locking a certain value. This can be a 20 or a 721 token. And what you're trying to do is create a private representation of this token, which is a commitment. It binds someone or anyone to a certain value. And in order to do that successfully, first you'd have to submit a proof as a user who wants to deposit this token. And the proof, of course, will have to be, I'd like to deposit an ERC20 token of 20 value. And this commitment that I want you to create will be the commitment that holds 20 in its value, as well as I'm the owner, so I am part of this commitment too, or I'm binding myself to this commitment using my public keys. You'd have other information such as salt and so on to also have this commitment created. Now, when that proof is successfully verified, obviously this information of what this new commitment is and the fact that this is now part of a Merkle tree and this root will be represented on chain. So that's essentially deposits. Now, transfers are a bit more involved, where you already have a commitment that you've created with your deposits. Now, you will have to spend these commitments to create some other new commitments for a recipient. And in order to do that, you'd once again have to generate a proof that says, I have a commitment which holds a certain value, and I am the owner of this commitment because I can create this commitment, and I have knowledge of all of the secret information that goes into creating the commitment. And indeed, this commitment is part of a Merkle tree. It's part of one of the commitments that is valid. And I have nullified this commitment properly. And once you nullify, you're also proving that the nullifier is indeed corresponding to the commitment that you just created, and you indeed have the nullification key to nullify this commitment. And then you have created some new token or a new set of tokens for whoever you'd like to send a payment to with a certain value and their public keys and relevant salt as part of this commitment. And you're also ensuring that there's no double spend in this whole transaction, which is that no new value was either created or destroyed. Everything that was inputted was exactly what you've created as an output. Now that's just a standard sort of private transfers being done with tokens. That's how you'd create a zero-knowledge proof statement for it. Now, you'll submit this proof, and on successful verification of this proof, of course, you will be adding the commitments that you've just created and the nullifiers of the commitments that you've spent. What you're not obviously adding is, or you're not providing to the world, is which commitments you've actually spent. So as a result, you're not really connecting people, you're not really connecting what were the commitments that were spent to what were the commitments that were originally created before that. So you have anonymity in terms of you're not revealing who it is that transferred a certain value. And you will also have anonymity of the recipient because nobody can see who received this as part of a commitment because that information is held inside the commitment itself or the newly created commitments. Now, one other thing we also do here is we do encrypt the values that is required for the recipient to spend their commitments, essentially information such as the salt that is required to create this commitment or the new commitment once again, and other supporting information such as what is the token ID or value or which is the PKD that, or public key that you've used to the recipient and so on. So a recipient will be listening to these events and then they can decrypt it with their key, and on a successful decryption that they know they are the recipients of a certain token, and they will store it. Now, very quickly, withdrawals are the opposite of what deposits do, which is you take your token back from the L2 contracts to your original L1 world. And what you have to do is part of what you did for transfer, which is show that you own a token, that this token is indeed valid and exists as a Merkle tree, and you've created a nullifier correctly. And in written, you will now make the value public of how much you'd like to withdraw, and you will be transferring that value to whichever Ethereum address that you'd like to send it to, either yourself or somebody else. Now, in this, of course, you will reveal the new recipient. So deposits and withdrawals are essentially not where you're looking for privacy. It's really during transfers, that's where you're looking for privacy. What I'd like to highlight now is everything I've mainly spoke about was how the very first iteration of Nightfall works. Now, Nightfall 3, which is the new iteration of which uses Optimistic Rollup, is a little bit different, but it's fundamentally doing this in the back end. So Nightfall 3 is a ZK Optimistic Rollup. So those are three different words here. We use ZKs for privacy part, and zero-knowledge proofs are used essentially to construct the proofs that I just described, the deposits, withdrawals, and transfers. Now, the optimistic part is where we gain lower transaction costs and some scalability too, as well as rollups. A combination of optimistic and rollup approaches is where we gain lower costs and higher throughput as well from. Now, everything with respect to transfer, when you create a transfer proof, what you're actually doing in Nightfall 3 is submitting a transaction to the smart contract or directly to your rollup provider, which is a block proposer, and they will in fact check the validity of your proof and if your construct or your transaction information is in fact correct. And after checking that, they are the ones who will actually be submitting this proof as a bunch of other L2 transactions, other transfers included, into an L2 block. So that part is the rollup part. And the optimistic part is the fact that you're really not computing any of the proofs on-chain anymore. You're really not computing what the new Merkle root should be from the commitments you've added. You're not really updating any nullifier set anymore on-chain. All of that state data is just optimistic in nature, which is you're just telling, this is a transaction I'm submitting, and this will be the new state as a result of this transaction. Now, please go ahead and just accept that information. If indeed this information is wrong, either because the proof is wrong or the new state is just incorrectly calculated and the proof will subsequently fail, you will then have something called, or someone called, a challenger, which is a stakeholder in this environment, who will challenge this proof and submit a challenge call as part of proving that this transaction was indeed wrong, in which case you will then roll back all of those transactions that are part of that block. Even though if it was just one transaction that was wrong, you'll be rolling back the entire block. That's just how the optimistic rollbacks work. So that is the optimistic version. This is just like an overview of what are the various approaches for privacy and scalability that we have today using optimistic and zero-knowledge proof approaches. So Polygon Nightfall falls under the category of using zero-knowledge proofs for privacy and optimism for predominantly the scalability purposes. A bit more about the current state of what Polygon does is it has about 12,000 gas per transaction. Now, that number will go down further. We're currently working on bringing that further. And about 94 transactions per second. So that is based off of calculating a 15 million average block gas and 12,000 being the gas cost that you use. We're looking at 94 transactions per second. Now, with every optimistic approach, we know that there's no instant withdrawals. You'd have to have a waiting period of 7 days. We circumvent that by using something called a liquidity provider approach, where I, as a user, would like to withdraw my transaction instantly, not to wait for 7 days. I will then pay an additional fee to a third-party provider who is willing to take on my delay onto themselves, where they will wait the 7 days of period that I would have waited and retrieve the token. They would take this wait and retrieve the token themselves. And in exchange, what they will do for this fee is give me a token of the exact same value immediately. So that's how we circumvent the problem of instant finalities, by using liquidity providers. Of course, with optimistic versions, you're really relying on a lot of crypto economics and fraud proofs, so you'd have to incentivize the various parties involved in here correctly. That is mainly the overview of what Nightfall does. But just to give you a bit more information about this, the various parties involved and how they interact, you'd have the transactors, who are the users who create deposits and transfers and withdrawals. And they submit the transactions directly to the block proposer, if this is the case of transfers and withdrawals. And if this is the case of deposit, they will then have to submit the transaction directly to the blockchain, only because deposits require whoever is locking a certain token to the private world to lock the equivalent ERC20 token to with the contract, the Polygon Nightfall contracts. So that has to be done on-chain every time. But the transfers and withdrawals are done off-chain by directly either sending it to the proposer, or they could also submit to the blockchain if they are happy to pay the additional cost. Now, block proposers will receive these transactions, check the validity of these transactions, and if it's all satisfied, store it in their mempool. And when it comes time for them to propose a certain block, they will take a bunch of these transactions in whatever order of preference they require, mostly profitability, I would say, and take these transactions and put them into an L2 block and submit this L2 block onto the mainnet, which is the Polygon Nightfall contracts that sit on top of Ethereum. Now, Polygon Ethereum contracts are optimistic, so they receive all of this information. They don't really execute any of this information. They receive block proposed data and just do the least amount of calculations that are required to ensure that they're storing this block hash-related information on chain, and then stay put, do nothing else other than that. At which point, Also, other than that, Nightfall contracts will let you do not just block managements of L2, but also the block proposals that you have. You'd have to register to be a participant as a block proposer by holding a certain stake, which will then be used to penalize in case you suggest a faulty block. You also have challenge verification being done by these contracts, where you challenge a wrong transaction, and you, if successfully verified, the challenger will receive the stake that's been put in by the proposer. Other than that, you also have challengers. Just like I said, they're continuously monitoring that L2 network, and they will submit the subsequent challenges as and when they see a wrong block or a wrong transaction as part of an L2 block submitted. Liquidity providers will also be continuously monitoring the L2 state, but their function is to purely provide liquidity to a user instantly during withdrawals, not necessarily to challenge, but they could also act as challengers if required. Now, a lot of the engine for block proposers, challenges, and liquidity providers is similar bit of logic, where they're continuously monitoring the state of the network. Whilst one is submitting a block, the other two are not just monitoring the transactions, but they will submit challenges if required. So a block proposer can also act as a challenger to somebody else's blocks proposed if required. You just have to turn on a flag that recognizes them as a challenger, and the sort of work that you will have to do is pretty similar, other than creating a challenge request, which is the one difference between the two pieces of work that a block proposer and a challenger has to do. Now, just very quickly to highlight how challenges work. If there is a L2 block, in this case, let's say number 55 or 56 is the one with a faulty transaction. In order to then submit a challenge, a user has to submit a challenge saying the transaction called TX1 inside 56 is wrong. So you'd have to submit the block, all of the transaction information within the block that's required, and prove how this is wrong. And on successfully proving it is wrong, you will then be removing not just the block that is part of this list of transactions, not just one or two, not just 55 and 56, but all the L2 blocks that come after that too. So the incentivization has to be such that you don't wait the entire 7-day period to essentially challenge, which is pretty much how that works. I will not go too much into the details. In terms of roadmap, we're currently going through the security audit process of all of this code. And in May or mid-May, we're planning to go onto the mainnet with a restricted set of values for ERC20 tokens. So you'd have, say, ETH with maximum value of 1 that you'd be able to deposit with and then transact with. You'd have other tokens like USDC and USDT and DAI and so on. So a list of tokens that you could do private transfers with. Sometime during mid this year, we're looking at having a bug bounty program as well, where once it is deployed, you would just request anyone who finds bugs to be able to submit bugs to and get a bounty for that. Finally, it's after a certain point of time, these restrictions in terms of values and for both deposit and withdrawals will be removed, so that anybody should be able to do higher value transactions if required. And there will be other features that are going to get added over time, where when we start off with, they will not originally be liquidity providers. We want to onboard them slowly, or onboarding multiple block proposers as well. So that's just going to be done in phases over the course of time. That is the link to the repository. It's in public domain, so that it sits on a CC0 license today. Now, okay, just for a very quick demonstration, what you see here is a very basic looking development wallet that we use. This is not necessarily how the final wallet will look. The final wallet is more, this is what Polygon will make it look like, beautiful and pretty and professional. If I were to probably use this, people would actually think I'm running some sort of scam to steal their funds. Yes, so this is going to be the actual screen with deposits, withdrawals, and sends. We currently have this running on the testnet, where you should be able to test this as well. It's just the link is not currently public for people to start using the testnet themselves. But it's been running publicly, or it's been running on the testnet since end of March. And this is a set of transactions that I've done over this period on the testnet, of course, and I'll explain why that is still pending in a moment's time. Now, very quickly, what I have here is a development wallet, once again I say, not one that will be live. That's an ERC20 token, and then you have an ERC721 token. And this obviously is running under development conditions right now. It's not using Godly testnet, it's just using a Ganache testnet for the sake of the demonstration. And it will also be quicker when I try to generate proofs, just because I'm not using the original proofs that take a bit longer. It's going to be much shorter in time frame because I use stop circuits to generate proofs here for the demonstration. So very quickly, I'm going to try and deposit 10. Alrighty. I will have to first approve the ERC20 contract to be able to transfer this for me. And the second bit is the actual transaction where I'm submitting the deposit transaction, which holds the proof and the corresponding data to the smart contract. That's what I've just signed. And you will see that I now have an L1 balance that is shy of 10 and pending deposits of 10. And it's pending because it's a roll-up. This is where not whatever I submit as a transaction will be immediately put into the smart contract. It will then have to be part of an L2 block. And for this demonstration, I made those 2 transactions per L2 block. In theory, you can have much higher, 32, 48, and even more blocks per transactions per block. So I'll just quickly do a deposit for a Nightfall ERC721 token. I'd have to approve and then sign the actual deposit as well. And you will see in a moment's time, I will now have a balance of 1 for ERC721. So what actually happened during this entire time is that there was a proposer listening to these transactions, and they've created a block with both of these transactions. And as a result, the pending deposits became finalized L2 balances because they have now been suggested as part of an L2 block. Until then, it was just waiting to be submitted as part of an L2 block, which is why they were pending. Now, to do a very quick transfer, I will do a transfer for 721. That was what I deposited, so I have token ID 1 available to me as part of 721. I'm signing this. I could now choose to send this transaction either directly to the smart contract or to the block proposer, but I've submitted it to the smart contract for the moment. None of the gas values that you see in the logic that I sign are actually relevant. You need to have a prediction for MetaMask written to give you a more precise gas values that you will have to pay. Now that's in pending because it's part of an L2 block. It's not yet part of an L2 block. So I will do another deposit to give it enough transactions for an L2. I'm submitting that transaction with the relevant proof. Okay, well now I have an L2 balance of 20 and 1 for myself. I wanted to do a transfer to some other account, but I forgot that I didn't have enough. I forgot to do that as a result of being shy on time. I will do a quick withdraw now, but the important bit is I want to do a withdraw with instantly, so I'd like a liquidity provider to be involved in this transaction. So you will see that I submitted a pending 10 for my withdrawals. I will just do another deposit for ERC721 to fill up the L2 block. Well, I don't know where MetaMask went. Now, that is funny. Either way, what I can tell you is something what I did not expect just happened. I always said for 5 years of my career, doing live tech demos is a career suicide. Today is mine. Anyway, I'll do another transaction. Now, it's a pending outflow. What I wanted to show was you would have had a liquidity provider who would have risen to this request and actually provided liquidity for me in order to be able to withdraw my transaction. So I would have immediately had a balance of 10 in L1. And another thing that I wanted to show finally was through a wrong block where it gets challenged and a rollback happens such that my transaction, which showed as final in L2, would have ended up back as part of pending because it went back to the mempool as a result of being challenged, and the transaction and the L2 block got removed and ended up back in the mempool once again. That was the fourth demonstration. I'm afraid that is everything I could do for the moment. I'm happy to take any questions if there's time.
Thank you very much. It was a wonderful demo, and I definitely applaud you for your bravery. I mean, doing a live demo is just amazing, right? I mean, we don't normally do that in this space, but it's almost worked. Any questions at that point? We've got a coffee break, which is next, so we don't have this small technical break. We can take 1 or 2 questions. We lost our box. Oh, yeah, it's on the back, you know.
Hello. So thank you very much. I'm not going to ask a technical question, but more general. As you are from UI, right? I wonder what is the interest from the institutional side or the legacy side regarding Polygon Nightfall? What's the interest?
For EY to do privacy work, you mean, or interest in?
For EY's partners, because like it's an internal project, right? It's internal research, and like what's the opinion and interest from your partners?
Yes.
The ones who you're selling the solution to, right?
Yes. Well, over the years, what we've realized is our biggest mission was actually to get enterprises onto this blockchain, and very specifically public blockchains. We did not want to do private permission blockchains just because we did not see how it would scale well. And over the years, the realization we had was not just that they were not too comfortable to do this sort of work, but also they could not do a lot of transactions that they want to do on chain because they do not want to make things such as, for example, one of the projects we do with Microsoft is a digital rights payment project where you'd have an Xbox. Every time you play a game on an Xbox, you'd have to pay the provider of the game a certain royalty. You have to pay Ubisoft some royalty or EA Games some royalty. But that sort of thing, it takes forever to settle. So we do have tokenization approach where you can pay royalties much quicker and instantly today. But that logic, just being on a public blockchain, will never work in the future if you want to do the same thing properly. This today is done in a quorum private Ethereum-ish fork blockchain, but if you want, when they want to move to the public world, they do not want to do this publicly in terms of revealing how much am I paying my game provider for every time a user plays a game. So you need privacy in that aspect, that's one. But we've also had lots of interest from other sorts of like supply chain use cases where people want to do this. We currently, I'm not sure we went public with this, but we work with one of the biggest petroleum firms out there, and they actually did an e-voting solution where, similar to Gitcoin or CLR fund, where you pay a certain money to a project based on how many votes the project has received, quantitative funding essentially. Doing that also you needed privacy, for example, and we've implemented that as a second iteration now. So these sorts of things, if enterprises want to be on the chain, you just cannot do public transactions, and that's why EY is tackling the privacy problem.
Thank you.
We've got time for one more. And if not, then, oh yeah, first one more on the back, over here. No, you have to throw.
I don't see who is the one? I don't see you.
Nice.
Thanks. Maybe you have solved that, or maybe not, but like, how would that look like if a block could be challenged after 7 days? And
well,
I have done a transaction or bought some whatever NFT, like would the NFT then vanish out from a MetaMask, or?
If you challenge a transaction after 7 days, one, you wouldn't be able to challenge it because it's beyond the 7-day challenge period, and you never want that to happen. That's going to be the least probable situation you want to create. So the crypto economics around how you pay and who you pay have to be steady enough to ensure that never happens. But if it's within the challenge period, of course, all of the blocks that come after the L2 block that was just challenged will also be rolled back, just because they're not part of the correct state history anymore.
Yeah. No, I was just wondering how that would look like if I buy something or an NFT or do some trade and then look the next day into my account, like from a usability perspective, and then
it's not, yes, that's very true. Your balance will now all of a sudden from one day to another, you'd wake up to it being lower. So it's not great UX design, and some of the ways we probably will look around is for fungible tokens, it's a lot more easier to solve that problem using sequencer-like approaches. But for non-fungible tokens, you could also do the same, but just gets a bit more involved. It's not something we've implemented today, but that will be one of the things that will be coming up as part of post mid this year or later this year.